Hi, this is our final presentation of the research question. How do we create a bio-inspired salamander robot which can traverse granular media using foldable robotic techniques? From the previous presentation, we have modified the design a bit and also added some experimental results which we would like to present now. Coming to the parameter ID and updated dynamics, we have conducted a bunch of experiments to estimate the values of the system parameters, such as the link stiffness, and link stiffness, joint stiffness, and the damping coefficients. So, to find out the link stiffness, we have actually taken a failure laminate that we used for the prototype, and we attached weights to one end of it and measure the deflection. To measure the joint stiffness and the damping coefficients, we use the tracker software, and to measure the drag coefficients, we used a pulley and a weight system to drag a plate of known area uh, on on a test bed. So as you can see, these are the final parameter values, and using these values, we updated the dynamics, which you can see over here. As you can see, we were able to unconstrain the system from the ground.
Now to go over our design optimization process. The two variables we decided to optimize for were leg segment length ratios and the body bending angle. We optimized them for force and speed. Optimizing them for force would allow us to maximize our servo's output, and optimizing for speed would allow us faster engaging and disengaging of the leg, increasing grip in granular media. The body bending angle was experimentally validated by running the system at different spine angles and then getting the craft average velocity. Based on experimental data as shown, 27 degrees was the optimal maximum bending angle. The maximum length of the entire length was constrained according to maximum robot size based on manufacturing limitations, and the maximum bending angle was limited based on our design.
The final device was made using the 5-layer laminate techniques learned in class. It is composed of cardstock paper, adhesive layer, plastic flexure layer, and then another cardstock paper level. Then cardboard was used for extra support and connection points. From the last presentation we did, we added the addition of the middle body and the servo mounting slots. Attachment to commercial off-the-shelf parts was actually pretty tricky. We were able to get a screw into the material with some damaging effects due to the laminate layers falling apart. So we basically added extra cardboard layers to reinforce the structure to make up for this. Pins were used at the joints so that it would allow the different segments to be able to still freely rotate about that pin joint. Here is the video of it completely working. It works, however, there's definitely some manufacturing and design decisions that cause the system to be not as good as it could be.
In conclusion, our design answered our research question. We were able to create a bio-inspired salamander robot that can move through granular media using the techniques of foldable robotics. This design and the research allows for a number of different branches to come off of this, including designs for beach and desert environments, since we've already shown that the salamander robot can operate in a sand-type media. It also allows for research into different types of environments, such as interplanetary robots, for instance Mars, where you have the Martian dirt that is a close analogy to sand, as well as undersea crawlers, where the material that the salamander robot would be walking on could shift underneath its feet. Each of those would have their own different research criteria in there, such as interplanetary robots dealing with the intense radiation, a little bit lower gravity, and the unique material of the Martian surface. Undersea crawlers would need to be waterproof, have a negative buoyancy, so they would always stay on the floor of whatever lake or ocean that they are on, as well as be able to operate in the material that they're walking on. For future work, we would start to look at the payload integration, so different types of sensors as well as the microcontrollers and battery systems to keep them operating off a tether. As you start to put these materials and these payloads inside of the robot, then you start changing the mass and the inertias of the different parts. As you do this, you need to start looking at the different dynamics that this creates to make sure that the robot continues to operate the way that you want it to.